Thank you. I'm Maya at Lawrence Livermore National Laboratory in the US. And the title is Purpose-Built IP for High Performance Computing. Note the question mark at the end. So I'm speaking from a little bit different perspective than someone's talk. So this is a combination of architecture and ideas about languages and trying to accelerate the very high end of computing. So exascale supercomputing has come into fore in the last year or so. And in the United States, in the Department of Energy, we have two machines, the Frontier at Oak Ridge and El Capitan at Lawrence Livermore that's being assembled now that are reaching greater than an exaflop. So here are some statistics about the various machines, but you'll note that while there's some innovation in the packaging and the cooling and the assembly of these nodes, they're nevertheless, when you come right down to it, commercial nodes. So AMD nodes, in this case, the EPYC, and then GPUs. So this is a lot of excitement that has come in, but I have to tell you, and I'm sorry this is being recorded, but while we have demonstrated greater than an exaflop, nevertheless, for the real codes, the multi-physics, the real work that's being done, we have to scale that way back so that these are commercial nodes, customized network, customized packaging, but ultimately we're not getting necessarily exascale performance on the problems that we really care about. So in conjunction with the hardware being built, the Department of Energy in the US also had this exascale computing project, and the idea was to build a software stack to try to compensate in some ways or to optimize for the machines that were being built. And so many of us, including my own projects, were involved in this exascale computing project that is building that software stack. But when you get right down to it, these are general purpose servers that we're using. So basically it's commercial data center server architectures. And what has been done over the years is that we invest in certain components like low latency, high bandwidth interconnect networks. So unlike the data centers where each, you're basically renting VMs and they're being migrated and you don't care where they go. In this case, you're trying to do a very large computation on one unit that scales to thousands of nodes. So the network does matter, and it does matter that you want low latency and high bandwidth. So that's something that has been invested in. And also influencing the architectural direction and accelerating timelines. So we had a number of programs like Fast Forward, Path Forward. Right now, it's the Advanced Memory Technologies program that's in a couple of phases. So we're trying to influence the direction, but still understanding that there's a lot of momentum from the commercial marketplace that the government can't really compete with. And we continue to code refactor and rewrite. So over the years, we went from vector to distributed memory parallel. There's been a massive rewrite that was really part of the exascale computing project to do GPU offload. And now it looks like we're going to AI engines. And so is this another rewrite to try to work with the commercial sector. And so this question was raised as a joint Department of Defense and Department of Energy question that can the microelectronics fabrication and packaging innovations that are going on in the past couple of years, and a lot of investment has been put into them, can they facilitate developing specialized IP that will work well for the HPC problems, the scientific problems? So is it possible to develop purpose-built advanced architectures defined through perhaps disruptive hardware design? So that was the question of the Project 38 that has been going on for a number of years. My question, which is right at the bottom there, is can it be cost effective? Because really that's what it amounts to, unless it's a very, very important special problem, it has to be cost effective. So in the spectrum from going from commodity server to fixed function, here's where we are right now with basically data centers, CPUs, general purpose GPUs, high bandwidth memory, network, high performance network. If we go into the AI ML domain, it's an old picture of a GPU there. So rather than the GPU, there's an AI engine. And of course, we're all familiar with fixed function, like for security functions, specialized blocks, that's what they do, and we invest in that real estate because we care about that particular function. So, of course, having specialized hardware blocks is business as usual for large volume. So like hash units, like for networking, compression, encryption, AI, not for low precision, FP16, specialized formats. The question that we were asking is, can it work for high performance computing? And the challenge there, and actually this started, the first meeting was in 2017 on this topic. And there were some people from the Department of Defense and then DOE working together to try to understand whether this could happen. And even though I've been involved in the Department of Energy for a number of years now, it struck me once again that the huge variety of approaches to scientific problems, going from molecular dynamics to radiation transport, and the algorithms keep changing. And then as you get new observational data, you get more insight and then you keep changing again. So you're continually changing the algorithms. It's really possible to figure out that there's some specialized IPs that in the long run are going to work out for you and really accelerate your computation. And so what you want to look at then is what is widely applicable. And of course, different sorts of matrix multiply, matrix vector operations. Lawrence Berkeley was looking at fast Fourier transform for certain forms of bioinformatics. What I'm going to describe to you now is work we did with programmable gather-scatter engines that was then used for key value lookup for bioinformatics, database lookup sort of application. And then floating point compression for the ZFP is a library developed at Lawrence Livermore. It's been around for a while. Last year, they won an R&D 100 award. So we were looking at building hardware pipelines that could do that kind of compression. And it's possible now with the advent of chiplets, which have been around for a while, but now can they become more general purpose? But chiplet mix and match make this feasible. So here's a little picture of notional picture of a chiplet where you have that substrate and customized connections or perhaps standardized connections between them. And a company that has taken off in trying to make chiplet-based breadboard, zero ASIC. So this is a picture from their web page where they basically give you the substrate and standardized communication between chiplets, and then a library of chiplets that you can put together and manufacture. So perhaps with chiplet technology, this sort of thing would be possible. So what I'm going to tell you about is some work that we did over the years in memory-centric accelerators. The reason being that we have been seeing more and more floating point with Intel. That's if it goes off chip, they don't care, but everything is off chip. So we've got memory walls. We've been talking about that for a long time. So we were looking at how to alleviate some of those problems. Then the ZFP hardware compression. As I go through that, I'll talk about, well, how do you interface to the CPU core when you have these specialized IP blocks and then you're working in a more general framework? And then no talk in any kind of forum like this is complete without whining about the tool chain. So I have to do that. Okay, so data movement. So data movement is a key challenge. Of course, you have to move the data, but don't move extra data if you can avoid it. And that's really the focus of this advanced memory technologies program. So figuring out ways of making memory more efficient and then also being able to move less data if you can. So this was the challenge that we went after. And sparse MATVEC is an example. And so our approach was this near memory programmable gather scatter engine. We called it the data rearrangement engine. And this is not meant for pointer chasing. This is meant for indexed operations. So A sub B sub I and nested if necessary, and then strided, which is what you see a lot. And then that was used as a building block for this key value query accelerator, which was used for this K-mer lookup. So K-mer is K-length genetic sequencing. In the biosecurity area, we have a problem where you might get a metagenomic sample, you scrape off the wall of the subway, and then, well, what is everything you're seeing in there? And so we have this enormous database. And so a way to look up K-length sequences in that. And probably not readable, but number of publications that came from that. So DRAM with HBM and at the time we were looking at this hybrid memory cube, lots and lots of channels. So the channels with wide access are really good for sequential, predictable and store. Caches help, but irregular applications like graph and other sorts of irregular applications really don't benefit. And what you end up with is a lot of data movement where you're not using the data. And so what we were trying to do is we operate on a batch of indices. We gather a dense view into a scratch pad or use it for the scatter. And then one of the added benefits, which we realized and others have realized, is that once you have that dense view, you can now vectorize. So something that could not be vectorized before can now be vectorized. So this picture is showing the strided axis, where we're gathering a dense view of an array into the left-hand scratch pad. The right-hand side is showing the sparse MATVEC sort of thing, where this is for page rank. You're indexing into an edge list to get the page rank of edges of nodes associated with a particular node you're looking up. And the idea is that our hardware would assemble that view for you. So this is the picture of the hardware that we were simulating. So we simulated this on FPGA UltraScale Plus. So our idea was, so the idealistic vision, which was not realized, or which has some problems, but the vision was that could we build a commercial HBM style of memory DRAM chip where the memory controller is on a logic layer and you have stacks of memory. And so it can work autonomously with different CPUs and do this gather scatter for you in the memory. So it's assembling the view and giving it to you. So this is the picture that we had. And in the emulation, we did the processors are the ARM cores on the UltraScale Plus and the DRE. So there's a switch, which they did have in the hybrid memory cube with they call the memory vaults. So that's the vision that we were going into. I'll go into why that didn't work, or it needs some more refinement. This is a little picture, I'll blow it up here, given a simplified power profile. We can see if you run on CPU only, that's the wide blue line going across. if you use the CPU plus DRE, you're spiking with the power at times, but it's much shorter. And then we also looked at a narrow, so suppose you didn't have the wide channels, but you had narrow channels, you have a tremendous improvement in the energy efficiency if you can do that. So, you know, we've presented this work before, and some of the CPU and memory companies have looked at it. And I think that the consensus seems to be for the narrow, that yes, this picture is very nice, but the amount of extra hardware you have to put in to support the narrow channel and the extra memory controllers is too much to make that commercially attractive right now. So API is very simple, set up either for strided access or indexed access, fill and drain. Now we come to all those details. So that was a nice simulation, but let's talk about reality. So we had an abstract view of the memory that we modeled, as I said, on the hybrid memory cube. And we did a latency-centric evaluation. So a lot of times, yes, you might have enormous bandwidth, but you're never going to realize that bandwidth because you have these dependent chain of fetches. So we're assuming that we have enough bandwidth. So that was the model. We were able to model two different types of memory latency. So at the time we were, and I continue to be interested in, for example, persistent memories that might have different read and write, wildly different read and write latency times, as well as DRAM. We had a simplified memory model, so a fixed latency, or later on we had a statistical distribution of latency. So you could put in a table and it would randomly pick a latency based on the table that you put in, like a Gaussian, for example. When you have a workload, that's what you end up with. And the memory sees a stream of read or write to physical addresses. So where does the address translation occur? Well, the scratchpad buffer on the memories, our scratchpad buffer was on the memory side, so it's holding physical addresses. And so one option is to route the addresses to be read or read, the virtual addresses through the MMU, but that's like involving a routing to the CPU. And our ideal was to do everything in the memory. So how do you do that? Because if you're doing this indexed access, you don't want to walk off the end of a page that and go into like memory you're not supposed to see. So in the prototype that we built, we used this contiguous memory allocation. It's something that's available in Unix. And what that allows you to do is when you build your kernel, you say, okay, I want this much memory contiguously allocated, and then what you're going to work with your arrays is within that, so you're guaranteed not to go outside that memory. But people are continuing to work on this problem, and there's in this month's micro, there's some paper that the contiguous memory helps in a lot of different applications, not just this one. And working with some of the vendors and commercial entities, as I've said, they look at not only our idealized vision of having everything within the memory, but you know, the caches are part of the memory hierarchy too. And so how do you make this sort of programmable gather scatter work within caches and scratch pads on chip? So there's a lot of different options there. It's a continuing source of ongoing work among the memory vendors and the CPU vendors. We also, one of the things you could do is improve the fidelity of the simulation for specific memory types. At one time, you could detect gather scatter patterns. So everything that we were doing was more or less, the programmer told us to do that. So I think I'm close to getting a little far along. So I will not tell you too much about this key value store lookup accelerator, except that we used two of those data rearrangement engines within there and built a pipeline. The sort of table is an open address hashing table. So you start at the address you hash to, and then go down a probe sequence length number of entries to find the entry you want. So that's what the pipeline supports. And we did a whole lot of evaluation with this K-MER database, which we happen to have because it's being used right now for bioinformatics, metagenomic sample applications. But I'm going to not tell you all. This is the slides will be posted, so you'll see all of this. But we did a whole lot of evaluation, and of course, it depends on how full is the table and what's the probe sequence length and what are the different latencies, and also we looked at all of that. But the key points to take away from this work is that the interface does matter. So you really do need a block of requests and responses to enable that efficient pipelining. Evaluation matters because there are certain conditions. If I hadn't gone so fast through that lookup accelerator, you would have seen that certain conditions, the software is actually better than the hardware. So when does it make sense to have that hardware IP? We spent a lot of time on this FPGA-based emulator, and it was really fast. So you could let it go overnight and just do a huge set of experiments and really be able to evaluate a lot. But we also found that it was for a single core. And so when we could combine it with a software simulator, we got new insights and we were actually able to improve the hardware by doing that. So let me just tell you a little bit about this compression for HPC. This is a different application. Again, we're trying to search for IP blocks that will work for high performance computing. And so this particular CFP library has been, I think, since 2014 or so. And then Peter just got this R&D 100 award last year for it. So what we did is to build a library called ZHW, which was a hardware pipeline for encoding and decoding the fixed rate. So CFP has lots of different options, but we were looking at the fixed rate encoding and decoding. This is showing you the pipeline of encoding and decoding with some analysis of how many cycles each block is going to take based on. So the key point about ZFP is that it's based on an array, so 1, 2, or 3D array. So you're compressing a block, so it's not a linear compression unless you're 1D, 2D, and 3D. You're compressing a whole block, and so the pipeline latency is based on the dimensionality. And this ZHW encoder was built as an IP block. It's we went through a long, sad story, which ultimately that turned out happy, so that's okay, of developing this, but we were able to synthesize, and that's 7 nanometer, 293 megahertz. So we comparing it to a RISC-V, Vision 5, which is an embedded RISC-V, but it's one we had. It outperforms that, but it's not, this particular implementation is slower than the Mac. But we were looking at, could we provide this encoder as a custom instruction issued by RISC-V core in an SoC? And so what we did is use this mosaic system on chip. So this is a tiled architecture, and each tile can either have a RISC-V or something else like a scratch pad. And so we said, okay, let's put the CHW encoder as one of the tiles. And so this is the framework mosaic is fully implemented in Verilog and runs on FPGA. And what we did is added the CHW encoder. So here's a customized instruction. So instead of doing all this in the RISC processor, you send it out as a custom IP instruction. So we added network. So there's a network on chip connecting the tiles, and we added network on chip encoder and decoder. But the important point that I want to tell you about is that we looked at 2 different ways of doing this custom instruction. So John Schauf really loves this direct message injects from one core to another. So this is this input mget are Q put and Q get. So this is message queue. So one core is directly sending to another core. The other core could be the ZHW core. And then we added this input and get, which is more generalized communication. And so we thought, oh, well, we've got this special instruction already there, Q put and Q get. Let's use that to tell this as a special instruction to tell ZHW to do its encoding. And what we found is that this direct message injection really worked very badly for our custom IP core. And the reason is it's dominated by memory. So here we were taking data from memory into the CPU, having the CPU send a message directly into the ZHW port with this round trip. Rather than that, just use DMA. So we ended up doing a third-party DMA where the CPU would say, okay, decode this block. It would tell the memory, start a DMA operation, but ended up on the ZHW. And that ended up having much, much better latency and throughput. So we ended up with a reasonable implementation and learned a lot about how to interface between RISC-V core and a custom IP block. Now my toolchain story. So we used, Scott, who did this work, used System C to design, because he wanted control over the timing, but he wanted to write in a modern language. And also, when you're talking about CPU plus custom IP, you really want to write in one language. So system Verilog, you have these two different things going on. So anyway, that's what he did. And come to find out that the Xilinx Vivado, the tool set would not accept the System C that we gave it, which they really acknowledged, but they weren't going to do anything about it. So we could never find out with the FPGA what is the real clock rate, and how can we make this thing real? And so we ended up writing a System C translator ourselves, and luckily we were able to leverage this work from Waterloo, who had already built in Clang. They understood System C and had all the System C constructs extracted out. So what we added was this System C tailored sort of abstract syntax tree that we would generate. And then we translate that into system Verilog. And so we were able finally to get the FPGA output of that. We have a paper that describes all of that. Anyway, so the back end is independent of Clang because Clang is its own learning curve. And it also allows other implementations that we haven't done, but we needed the system Verilog. So anyway, with our compiler, we were able to get FPGA. We used the Silicon Compiler Open Road toolchain. So with a lot of effort, we were able to go through this ASIC toolchain. And I've run out of time completely, sorry, but I won't tell you about all the woes of trying to get through that toolchain, but we did it. And so we have some numbers, and it's really not as fast as we want it to be. And the reason for that is that we wanted to be completely true to the software. So you could take floating point numbers, encode them in our hardware pipeline, end up with a big bit stream, and then decode that bit stream in software. It was completely compatible. That was our goal. That's what we did. It ended up being slow. So really, what this has taught us, we have to do hardware algorithm co-design because there's a long dependent tool chain that long dependency chain that it results in a long critical path, especially in the decoder. And that was the reason for how slow it is, 31 megahertz. So here are all the people. I wish I had all the pictures because Scott did the major part of the hardware design and had some very talented students also working on this. And so I'll leave you with our thoughts that, yes, we can do these HPC-centric hardware modules. We have to pick them carefully. We have to do hardware software co-design. And the question is really up for discussion, is it economically worthwhile to do it?
Thank you very much. That's a very quick question. Settings. Please.
Even like a massive push, so ZFP starts to look a bit like blocked floating point stuff that's coming out of machine learning, or great enthusiasm for building loads of hardware for low precision. I want to be like algorithms and scientific computing really changing to fit that kind of modern push, because we're not doing rounding all the time. We do a bunch of operations and then do rounding really late to get the point of killers.
No, that is a really interesting question. You were talking about reduced precision floating point. And so I saw, I saw a paper on that recently where they were doing it for a specific HPC scientific application. What they found is that the majority of what's going on, you have to have double precision or it breaks. So that, but there's this one place where they could use precision, but then when you actually looked at what they were doing everything in double, then they were changing it to the 32 or 16-bit to compress it, to save space, and then convert it back when you were actually going to use it. And then they were doing analysis of the areas that you might have. So, no, I don't know whether they can.
Let's thank Maya again for an excellent talk.